We're going to take a look at ALEKS Homework 6, this problem analyzing the electrolysis of molten salt. This is similar to the very first type of electrolysis problem that I went over in section 18.7 in your notes. And it's just, this one is, I feel like these problems might be a little bit tricky until you get the pattern of how to solve them. So we're going to work on a couple of them together. And so here it is telling us that we have aluminum oxide, Al2O3, and it is asking us to come up with the half reaction for the reaction that's taking place at the anode. It wants an overall reaction, and it wants us to identify which is the anode. So let's just remind ourselves of what's going on with anode versus cathode and things like that. We have, to help us remember, we have red cat. So that tells us that the reduction is taking place at the cathode, and that means that the oxidation is taking place at the anode. And then we have oil rig, oil that helps us remember oxidation is loss. So in an oxidation reaction, electrons are being lost. So they're the product or one of the products of the reaction. And reduction is gain. So that helps us remember that in a reduction reaction, an electron is a reactant. It's being added to something. So when we look at the diagram, we can see the flow of electrons. They're moving from A to B, electrode A to electrode B. And that tells us that electrons, they are leaving A, the electrode A, they're leaving A and they're moving over and they're being added down onto electrode B. The electrons are leaving A, and so that means that A is the anode, because the anode is the location where electrons are being lost. So now we want to figure out a balanced equation for the reaction that takes place at the anode. That means we're looking for the oxidation. It's probably helpful for us to write the overall reaction first and then divide it up and figure out which one is the oxidation. So in the overall reaction, if you kind of refer back to your notes, we have our ionic compound, and it's liquefied because it's molten or it's liquefied. So there's our ionic compound, and that is our reactant. And then the products of this reaction, we're separating the ionic compound and turning it into pure metal, in this case pure aluminum, and the non-metal, which in this case is going to be oxygen as a gas. Now, one thing that's different about how Sapling wants this, Sapling wants you to take that ionic compound, aluminum oxide, and it wants you to write it as cations and anions. So that means it wants aluminum cations, and they are still liquefied, and it wants oxygen or oxide anions. Actually, I'm going to move that over because we're going to need to balance this. So I'm going to leave some space for coefficients. O2 minus, so this is also liquefied oxide anions. It's kind of weird to look at. And our products of this reaction are going to be the aluminum metal, which is still going to be liquefied because it's a really high temperature. And then our other product is going to be the oxygen in its natural state, which is O2. So for the most part, these nonmetals, they exist as diatomic molecules, meaning that you have two atoms in the molecule. So what we need to do now is balance this equation that we have here. It looks like we're going to, because of the 3 and the 2 and the oxygen, it's going to be a little tricky to balance. But you've balanced enough equations, you're probably really good at it. So there's the stoichiometric coefficients. We can fill in how many aluminum ions do we have? We have 1, 2 times 2. That's 4 aluminum ions. And how many oxide ions do we have? 2 times 3 is 6, so that's a lot. And our products over there are 4 aluminum liquids and 3 O2 gas. So we've got 2 of the 3 parts of this problem figured out. The last thing that we need to figure out is writing a balanced equation for the half reaction that takes place at the anode electrode A. So that's going to be our oxidation reaction where we are losing electrons. So here we want to just kind of like focus on what am I looking at for my aluminum. I have aluminum cations going to aluminum metal. And what does that look like as a half reaction? You could look it up in your table of half reactions. You could find this reaction if you wanted to. Or you could just write it out, figure it out. So here's our aluminum half reaction. And that is definitely a reduction because the aluminum is gaining electrons. So that is not the reaction that's happening at the anode. So that means that our oxygen reaction is the one that's taking place at the anode, and that reaction is 6O2 liquid turning into 3O2 gas. And we're also going to be spitting out 12 electrons. And my suspicion with this problem is that ALEKS is not going to be thrilled about the stoichiometric coefficients that I'm using in this equation right here. It probably wants me to simplify. I don't know for sure, but these problems are so tricky that I really don't want to take a chance. So I think you're going to want to enter it in with the lowest possible stoichiometric coefficients. So this would be what you would type in. And there's your answer.